Most of us still think of AI as a chat box on a screen. You type in a prompt, and it types back an answer. But that standard model has a hard limit. It relies entirely on static, pre-trained data to guess the next word in a sequence. It is trapped inside its own training, completely disconnected from the live, physical world. Now, put that same technology on a busy manufacturing floor. Imagine a massive robotic arm on the main assembly line suddenly freezes and powers down. In this exact moment, a traditional chatbot is useless. It cannot read the live telemetry data coming off that machine, and it certainly cannot coordinate a physical response across the factory to fix it. Solving a multi-step industrial failure requires a system capable of executing a physical response, moving from passive dialogue to direct intervention. That brings us to the AI agent. This is the evolutionary step up from a passive language model into an autonomous digital system. Instead of waiting for your text prompt, an agent can observe a live situation, reason about what is happening, and execute a multi-step plan to reach a specific goal. To pull this off, agents use something called tool calling. When an agent realizes it lacks information, it reaches outside its internal memory. It can ping external databases, read live factory sensors, or connect to an API, an application programming interface, which is just a bridge that allows different software programs to talk to each other. Giving an AI the ability to independently select and use these external tools is the specific shift the ACT framework, which stands for reasoning and action. This diagram shows the REACT loop, breaking the agent's logic into 3 distinct phases: observe, reason, and act. Let's apply this to our broken robotic arm. In a massive factory environment, you rarely rely on just one single AI. Instead, companies use multi-agent systems. This means deploying multiple smaller agents, each highly specialized for a specific task. You might have one agent dedicated entirely to supply chain logistics, while another focuses strictly on managing the inventory on the factory floor. These specialized agents communicate autonomously. If one agent is missing a piece of the puzzle, it can query another agent to fill in its knowledge gap. For example, if the supply chain agent detects that a shipment of raw steel is delayed by 2 days due to weather, it immediately alerts the production planning agent, which then automatically adjusts the daily manufacturing schedule to compensate. By passing information back and forth like this, multi-agent collaboration acts as an active nervous system, aligning fragmented departments in real time. But to be clear, in an industrial organization, these AI agents are deployed to coordinate and assist. They do not replace the human workforce. Instead, they provide deep decision support. This diagram shows how an agent can instantly synthesize data from a bottlenecked assembly line and recommend the safest, most efficient response directly to a floor manager's workstation. They also excel at knowledge retrieval. During a crisis, an agent can save a human technician hours of searching by instantly guiding them to the exact repair procedure hidden deep within a technical manual. Agents can even take on long-term sustainability roles, continuously monitoring facility-wide energy use to pinpoint waste patterns or identify circular material reuse opportunities that a human operator might overlook. The value of an AI agent is reducing delays and cognitive overload. It handles the frantic data gathering, allowing human experts to focus on complex judgment and physical execution. Of course, these systems have strict practical limitations. An AI agent's usefulness is entirely dependent on the quality and reliability of the organization's underlying data. If the internal data is fragmented, or if the user gives the agent an unclear goal, the system can get stuck in an infinite feedback loop of redundant tool calls, or worse, recommend the wrong physical action. This is why high-stakes environments rely on a safeguard known as human in the loop. In practice, this means an agent can research, plan, and recommend a critical operational change, but a human operator must review the logic and provide final approval before anything is actually executed. By connecting fragmented systems and shifting from passive analysis to active problem-solving, AI agents safely elevate industrial teams, moving manufacturing away from reactive delays toward a faster, more autonomous workflow.